gearing. So we go for gear ratios when we want to increase the speed. Okay, so if you don't want to get the speed which is equal to the speed of the motor, okay, then in order to increase the speed, you can go for gear ratios. Okay, which you are familiar with. In many NC systems, the lead screw is driven through a gearbox. The gear ratio, that is denoted by kg, is defined as the ratio between the speed of the lead screw to the speed of the motor. Okay, if you go for higher gear ratios, you can get higher speeds. So gear ratio, it is given by angular velocity of the lead screw to angular velocity of the motor, that is speed of the lead screw to speed of the motor. And then if you want to find out moment of inertia J, okay, for that also there is a equation. J is equal to Jr plus kg square JL, where Jr is the inertia of the rotor and JL is the inertia of the lead screw. Okay, this is required to know. Okay, so what is the moment of inertia? Okay, so for the lead screw and shaft of the motor, which are coupled together. In order to find the overall moment of inertia, so you can make use of this equation. Okay, next stepping motor or stepper motors. Stepper motor is an incremental digital drive. Okay, earlier also we discussed about stepper motor. So when we discussed open loop and closed loop system, we discussed about stepper motor. Okay, it is an incremental digital drive. That means if you give one pulse input, that will result in achieving an incremental movement of one step angle. That's why it is called as incremental digital drive. So stepping motor rotates one angular increment or a step for each input pulse. Okay, suppose if you give one pulse input, that will result in a movement of one angular increment. So it will be equal to step angle. Okay, if the step angle of a particular stepper motor is 1.6 degree, then if you give one pulse input, so that will result in an angular increment of 1.6 degree. Next, the shaft position is determined by the number of pulses and its speed is proportional to the pulse frequency. So again, since for one pulse you are getting an one incremental position. Okay, if you are able to supply more number of pulses in very less time, you can achieve greater speeds. The shaft speed in steps per second is equal to the input frequency in pulses per second. So these are used as the drive devices in open loop NC systems and are suited for driving small point-to-point machines. So in earlier class also we discussed. Okay, so when we are discussing about open loop and closed loop control systems, so we discussed about why stepper motors are suitable for open loop. Okay, that we already discussed. Okay, next we need to solve a problem related to stepper motors. Okay, so here there is a graph related to torque versus stepping rate. Okay, so this is a graph of torque versus torque on ordinate or y-axis and stepping rate, that is steps per second on x-axis. So here this curve, that is L, denoted by L. Okay, this will give us an idea regarding or information regarding what should be the starting speed. Okay, so when you are able to start the motor, okay, after how many pulses input the motor will start. Okay, that you are going to get with the help of L. So whereas with the help of this curve, we are going to get an idea regarding running speed, maximum running speed. Okay, so this is the starting speed of the motor and this is the maximum running speed. So the region below this curve represents start and stop region. That means, so suddenly you cannot stop, go for stopping a motor. Okay, so at high speed, if you stop a motor, so that will have consequences. Okay, that's why start and stop region will be below this. That means you have to bring the speed of the motor to a certain level, then you should stop the motor. Okay, so that we'll discuss. So the torque versus stepping rate characteristic has a major significance in the design stage. Torque always decreases with an increase in the stepping rate. So here you can see initially when the stepping rate is very low, so torque will be high. So when stepping rate increases, torque is decreasing. The exact shape of the curves depends on the driving unit and the stepping motor itself. The upper curve, so that means this curve shows the maximum running speed. So this will represent maximum running speed of the stepper motor. Whereas the lower curve, that is denoted by L, shows the maximum allowable starting speed of the motor. Okay, this is the maximum allowable speed at which motor can be started. Starting, stopping or reversing the direction of rotation are not permitted in the region below the lower and the upper curves. So that means the region above L and below U, that means in this region starting and stopping the motor is not permitted. Stop accurately, first the pulse rate, that means input to the motor, should be reduced. To stop accurately, first the pulse rate must be gradually reduced to the rate prescribed by L and then stopped. Okay, so this graph will give you an idea. Okay, what should be the input? Okay, when you want to stop the motor. Okay, so from what level to what level you should decrease the speed of the motor before stopping it. Okay, all those things you can understand with the help of this graph or with the help of these two curves. Next, there's a problem related to this. The torque speed characteristics of a stepping motor drive system are as follows. That means, so the lower curve L, that is given by this equation, torque is equal to 200 minus 0.050 volts. Upper curve is given by this equation, T is equal to 200 minus 0.025 volts, where T is in Newton meter and V is in, that is speed, is in steps per second. The motor is loaded by a constant torque of 70 Newton meter. Calculate the maximum allowable starting speed and running speed of the motor. Okay, as we discussed earlier in previous slide, starting speed, okay, is given by lower curve L. Okay, maximum running speed is given by U. Okay, in the previous slide. Okay, so L will give you maximum allowable starting speed. So whereas U maximum running speed. Okay, so now in order to find maximum allowable starting speed, so you should make use of this equation, equation L. Okay, where V is the speed, V is in steps per second, that itself is the speed. So T value is given 70 Newton meter. Okay, in this equation, substitute T as 70 and find out V, that itself is starting speed. Okay, next, if you want to find out maximum running speed of the motor, next, in order to find maximum running speed of the motor, you should go for U curve, that is represented by this equation. T is equal to 200 minus 0.025 volts. Okay, now in this equation, substitute torque, you will get so max running speed of the motor. Okay, so like that you can find starting speed and running speed. Next, so the motor runs at the starting speed during first 13 pulses. What is the starting time period? That means in order to start the motor, okay, you should input 13 pulses. Now what you should find is, so what is the time taken to give 13 pulses input? So that is the starting time period. Okay, so these things you should find out. Okay, first if you consider the maximum allowable starting speed, that is denoted by this lower curve. Okay, that means this equation. So here torque value is specified in the problem. So substitute torque as 70 Newton meter. So then V is the unknown, that itself is the speed. okay, you will get 2600 steps per second. That is the maximum allowable starting speed. So that means, so you should start motor within this speed limit. Next, the running speed is determined by upper curve u, that is given by this equation. You can now substitute t in this equation. Next, v is the only unknown. So v is 5200 steps per second. That means this is the maximum speed at which you can run this motor. Next, during the starting period, the frequency is 2600 pulses per second. That means while starting the motor, you are giving the input 2600 steps per second. Now, so in the problem, they ask you to find what is the starting time period. That means what you should find is, so for 2600 pulses, it is taking 1 second. Next, for 13 pulses, how much time required to give 13 pulse input? What is the time required? You know, per second you can input 2600 pulses during starting stage of the motor. Okay, now, so you can find this value. So 13 by 2600 will give you the time required to start the motor. Okay, that means 5 milliseconds. Okay, so if you provide 13 pulses input, the motor will start. In order to supply these 13 pulses, 5 milliseconds is required. Okay, so this is like this. You can do calculations. Suppose if you want to select a stepper motor for particular application where you know torque requirement, okay, and other parameters. Okay, so you can do this calculations. Next, feedback devices. Okay, so in NC systems, so most of the NC systems are closed loop systems. Okay, so we make use of feedback devices. There are two types of feedback required: position and velocity feedback. Okay, in a closed loop system, information about the output is fed back for comparison with the input. These are directly coupled to the machine lead screw and the robot axis, and they provide position and velocity signals. Position feedback device, these are some of the examples, and these are included in the syllabus: encoder, resolver, inductocin, velocity feedback devices, tachometer. Okay, we are going to discuss about working principle of these 4 devices. Okay, first consider encoders. Encoders are position feedback devices. Okay, in you can find linear encoders and rotary encoders. So for our discussion for this course, we will consider rotary encoder. Okay, the rotary encoder is a shaft driven device delivering electrical pulses at its output terminals. The pulse frequency is directly proportional to the shaft speed. There are 2 types: incremental encoder and absolute encoder. Okay, this is incremental encoder. So in case of incremental encoder, it will consist of a single set of strips. Okay, so here this strip consists of gray and transparent area. Okay, black and white, that means transparent and opaque. Alternative transparent and opaque segments are there. Okay, and it will consist of a light emitting diode and photocell. Okay, so then whenever this photocell receives light, that will be converted into an electric signal. Okay, based on that, so you will get the output of the encoder. Okay, that will be in the form of analog signal. So that will be compared with the input in the closed loop. So then based on the decision will be taken by the comparator. Okay, this incremental encoder. Okay, it contains a glass disc mounted on the shaft and marked with a precise circular pattern of alternating clear and opaque segments on its periphery, like this. A fixed source of light is provided on one side of the disk. This is the light source, and a photocell is placed on its other side. When the disk rotates, light is periodically permitted to fall on the photocell. That means, so whenever light ray falls through this transparent strip, okay, so it will be received by the photocell. Whenever it is obstructed by this opaque strip, okay, photocell will not receive this signal. So when the disk rotates, light is periodically permitted to fall on the photocell, which consequently produces a sinusoidal output signal in the millivolt range. So that means it will be like this waveform. Okay, so rising and lowering like that. Okay. So then this signal is amplified and fed to Schmitt trigger circuit, which converts it to a square wave with suitable rise and fall time. So actually this is how the signal will be generated using encoder, okay, using incremental encoder, then using Schmitt trigger circuit. So you are converting it into square form, okay, the sinusoidal wave is converted into square form. So based on the, again, the input to the motor is also in the form of electric pulses. Now you can compare. So this output from the encoder with input to the motor. If there is difference, then you need to take action. If there is no difference, that means so it is okay. So everything is according to plan, or it is working properly. Okay. Next, disadvantages: false counts due to noise or disturbances, gross errors due to power interruption. These errors are eliminated by using absolute encoder. So these are some of the limitations with this. Okay, so the noise or disturbance, it is related to electric signal. So power interruption, again in between is power interrupt. Okay, then again there will be no feedback, so that may result in some error. In the video you can see the working principle of this encoder. Okay, this is the working principle of Okay, so this is the working principle of incremental encoder. Okay, this is the rotating disk, and this is the light emitting diode or light source, and this is the photocell. Since this encoder disk, okay, it is coupled to the motor shaft. Okay, so since it is directly coupled to motor or lead screw, okay, when there is rotary movement of the lead screw, okay, obviously that will result in rotation of this disc. Okay, and then based on rotation of the disc, so this graduations will be counted. Based on that, a signal will be generated. Okay, next, absolute encoder. So compared to linear encoder in absolute, so you have multiple disks. Okay, so absolute encoder. So absolute rotary encoder use a multiple track disk. Okay, in the previous case you can see a single track with alternative transparent and opaque segments, whereas in case of multi-track disk, so it is having different pattern. Okay, where each combination will result in a particular code. Okay, if suppose in this example, okay, for example here there are 4 tracks. Okay, 1, 2, 3, 4. Okay, so here you can see all 4 segments are transparent. Here only 3 are transparent, 1 is opaque. Here, so first 2 inner 2 tracks are okay transparent, so this one is opaque and outer track is transparent. So like that it will convey a certain meaning, and this can be converted into a binary code. Okay, suppose if you are considering opaque as 0 and this transparent segment as 1, okay, you can convert it into a binary code, okay, like 1110. Okay, so like that you can directly convert it into a binary code. Absolute rotary encoders use a multiple track disk which defines the shaft position by means of a binary word or another code such as gray code. Okay, suppose relative to the shaft position, okay, you will based on the in the this code, okay, you will get an idea where exactly the shaft is located. Even you can get the angular positions, incremental positions exactly. Consists of a lamp and photocell. So similar to previous one, a photocell is provided for each track on the disk. Okay, in this case there are 4 tracks and there are 4 photocells. The output from all cells give the actual shaft position in coded form. Again, so with the help of this one more video, you can understand how it will. Okay, here you can see. So there are 3 tracks. Okay, so in this absolute encoder, there are 3 tracks. So 1, 2, and 3, and that's why there are 3 photocells. So here 3 sensors. Okay, it consists of okay, it consists of 3 tracks, 1, 2, and 3. Okay, here you can see. So it consists of 3 tracks, 1, 2, and 3. So now again it consists of 3 sensors. Okay, here now you can see. So there are 3 sensors, photocells. Okay, so here only in 2 tracks. Okay, light is passing through only 2 tracks. Okay, because they are transparent. Now you can see the binary code. So 110. That means, so in track 1 and 2, okay, there will be light can pass through 1 and 2, whereas 3 it is opaque. Okay, that's why it is 0. Okay, like that for every position. So there will be a binary code. Okay, now we can see. So light is passing only through this track. So that's why binary code 100. Like that, it is continuously changing. Yes. Okay, so this is the difference between incremental and absolute encoder. Okay, so compared to incremental encoder, absolute encoder, so you can get the exact position. Okay, next resolvers. Okay, this is also a position feedback device. Okay, it consists of rotor and stator. Okay, for rotor there are 2 coils, and for stator also there are 2 coils. Okay, so VA and VB are related to rotor, and V1, V2 are related to stator. These 2 are stator coils and these 2 are rotor coils, and this circle represents rotor shaft. This circle represents stator shaft. resolvers have same general construction features as small AC motors. They consist of a rotor and a stator, both having two windings at 90° to one another. Okay, so here, so these two are rotor. Okay, so this coil, this is one coil related to rotor. This is one more coil related to rotor, VA and VB. So they are at 90° to one another. Similarly, these two are stator coils. So this is one stator coil and this is another. Again, these two are kept at 90° and this is the shaft of the stator. Stator means it is a fixed element. Rotor means it is the rotating part. NC systems, the resolver is used as a shaft position measuring device. That is, it is also used to get position feedback and is directly coupled to the lead screw of the machine tool. In NC applications, only one of the rotor windings is used and it produces the feedback signal VA. Though there are two windings, so in NC systems only one is used, that is VA. The phase angle which is contained in the feedback signal depends on the angular position of the rotor shaft. So this phi is the phase angle. It depends on the angular position of this rotor shaft. The rotor is continuously rotating with an angular velocity omega O. The feedback signal is given by this. This is the equation. Yes, that means a signal will be generated which is corresponding to this equation. Sinusoidal voltage of the rotor is converted into a square wave, like we did in the what we discussed in previous topic. Okay, so using schematic trigger circuit. So with the sinusoidal voltage of the rotor is converted into a square wave and compared with the square wave corresponding to the stator voltage, which is used as the reference signal. So that means, so you are comparing these signals with the input. If there is difference, again you are taking corrective action. The comparison is performed by a phase comparator circuit which detects the phase shift between the reference and the feedback signals and generates a corrective signal. Okay, so